What the Sun may do to the Earth in 2025. The planet Earth was assaulted from space on March 13, 1989. A catastrophe occurred, leaving millions of people without electricity and causing extensive damage. Although one might presume that this was the result of an unnoticed alien attack, a solar storm is far more likely. In Quebec, where an estimated 6 million people lost power, the effects of the solar storm were particularly devastating. Imagine waking up to a frigid home, closed businesses and institutions, and even the Montreal Metro having to cease operations during morning rush hour. Adding insult to injury, the airport was compelled to close its doors. The effect was genuinely enormous. This solar storm occurred during solar cycle 22, which is typified by increased solar activity. These cycles occur every 11 years on average, and scientists predict that a comparable event to the one that occurred in Quebec could potentially occur again by 2025. As you will see at the conclusion of this video, every metal has two faces. Follow along in this video to learn more about it. Hello everyone, welcome back to Zeey. Subscribe to our channel and ring the bell so you won't miss any update. Importance of the Sun. In the vast tapestry of the cosmos, the Sun's significance for our planet Earth is unparalleled. It is the radiant focal point, the beacon of life and the architect of the rhythms of Earth. Its influence extends beyond the celestial domain and permeates every aspect of our existence. In this video we will explore the Sun's multifaceted roles, which influence the very essence of life on our blue-green planet, in order to discover its profound significance. The Sun's function as the ultimate source of energy for life on Earth is fundamental to its utmost significance. The Sun emanates an endless stream of light and heat through the process of nuclear fusion, illuminating the cosmos and bathing our planet in life-sustaining radiation. This energy is harnessed by the biosphere of the Earth, initiating a series of processes that drive photosynthesis, the foundation of terrestrial life. Photosynthesis, which is orchestrated by a vast array of plant life, converts solar energy into chemical energy, giving vitality to Earth's ecosystems. This process is what provides our planet with the oxygen we breathe and the food we ingest. In essence, the Sun is the cosmic motor that drives the life cycle on Earth, sustaining a complex web of interdependent organisms. In addition to its function as a source of energy, the Sun is the master conductor of Earth's climates and seasons. Its rays, which strike at varying angles throughout the course of the year, regulate the ebb and flow of temperature and weather patterns. The inclination of the Earth's axis relative to its orbit around the Sun bestows upon us the symphony of seasons, including spring's awakening, summer's warmth, autumn's harvest, and winter's respite. These seasonal changes shape the landscapes and habitats in which life thrives. They influence the behavior of flora and fauna and direct the life cycles of numerous organisms. In addition, the Sun's radiant energy powers the water cycle, a fundamental force that maintains the delicate equilibrium of the Earth's ecosystems. Astrophysics of the Sun. The Sun's enigmatical nature has long captivated scientists, driving astrophysicists to uncover its secrets and gain a deeper comprehension of its complex life cycle. Decades of exploration and discovery have yielded significant insights into the composition and structure of the Sun. The Sun, like other stars, is a vast sphere primarily composed of hydrogen and helium. With a diameter of 1,400,000 kilometers, it is 109 times larger than the Earth. Despite its enormous dimensions, the Sun's unique composition makes it 4 times less dense than our planet. Contrary to conventional belief, the Sun is not merely a glowing gaseous mass that can be observed through a telescope. Similar to Earth, it has distinct strata with varying temperatures, each with its own distinctive characteristics. To better comprehend the Sun's structure, it can be imagined as a gigantic onion, with its nucleus at the center and successive layers superimposed upon one another. The core is the primary source of the Sun's energy, boasting an extraordinarily high temperature and enormous density as a consequence of extreme pressure. These conditions are optimal for the occurrence of nuclear reactions. The Sun produces helium primarily through the fusion of hydrogen. However, secondary nuclear reactions generate trace quantities of heavier elements such as carbon, oxygen, and nitrogen due to the extreme temperatures and pressures within the core. Within the interior, temperatures can reach a staggering 15 million degrees Celsius. The core-generated energy must then be transported to the neighboring regions. This is accomplished via radiative transport, in which radiation-based energy interacts with particles in the encircling environment. Some atoms within the radiation zone are capable of withstanding these conditions, absorbing and storing energy before emitting fresh radiation. This facilitates the transfer of energy between atoms as they traverse the radiation zone. Within the radiation zone, temperatures range from 7 million to 2 million degrees Celsius. Once the energy departs the radiation zone, a new mechanism is required to transport it to the surface of the Sun. Outside of the radiation zone, temperatures are comparatively cool, facilitating the absorption of energy by atoms. As their environs are cool and dense, however, these atoms do not readily release energy. Consequently, the transfer of energy via radiation decreases significantly. The energy is instead transported through the convection zone. Atoms absorb heat and ascend through this zone, eventually transporting the energy to the photosphere, the Sun's visible surface. The temperature in the convective zone decreases further, reaching between 2 million and 6,000 degrees Celsius as one moves from the radiative zone toward the photosphere, the Sun's visible surface. The Sun is constantly shifting. The photosphere, the Sun's visible surface, is our portal to the marvels of our star. Through this one-of-a-kind aperture, photons generated in the Sun's core are able to depart and travel across the universe, eventually reaching our eyes. When we gaze upon the Sun, we are greeted by light particles that have traversed the depths of space for longer than we can comprehend. Therefore, the photosphere is not only a component of the Sun, but also a link to its grandeur. However, early astronomers did not always have access to the photosphere. Their primitive telescopes were incapable of investigating the Sun's astrophysics due to their blinding brilliance. Attempting direct observation of the Sun would have caused irreparable eye injury. However, as time passed, astronomers developed a solution: specialized filters that improved the Sun's visibility. Through these filters, the presence of granules on the photosphere was discernible, resembling a pot of boiling water dotted with small, moving bubbles. Each of these granules is approximately 1,000 kilometers wide, dwarfing our own planet. Intriguingly, these luminous granules were frequently accompanied by sunspots, a contrasting phenomenon. Under the influence of powerful magnets beneath the Sun's surface, these dark blotches emerge. Compared to their environs, they appear cooler and darker, attracting the attention of astronomers. The cycle of bright granules is followed by the mysterious apparition of sunspots. Sunspots are created when magnetic field lines below the Sun's surface pierce through its photosphere. Occasionally the Sun, perhaps in a particularly ebullient mood, provides us with spectacular displays of solar flares and prominences. Solar flares, resembling miniature fireworks composed of minute particles, adorn the Sun with vibrant hues and emanate a unique type of light. In contrast, prominences appear as mesmerizing loops of fire that gracefully move above the Sun's surface, resembling a celestial crown adorning our star. Faculae, the radiant regions that punctuate the photosphere, are also present. These regions emanate a brilliant glow that distinguishes them from the rest of the Sun's surface due to their intense magnetic activity. In fact, the photosphere is a stage teeming with activity and intriguing revelations. Here the Sun puts on a spectacular show that reminds us of its inexhaustible marvels and enticing mysteries. Nevertheless, if you pointed your telescope at the Sun at random times, you might not see anything. In other words, there are times when the Sun's photosphere is nearly devoid of features, and other times when it is abundant with them. Astronomers have long pondered and investigated this phenomenon and have concluded that the Sun undergoes cycles. Solar minimum and maximum. Indeed, our luminous celestial neighbor is anything but inert. For instance, sunspots wax and wane periodically, as does the magnetic field, which literally reverses its orientation every 22 years. The Schwabe cycle, named after the Swiss astronomer Samuel Heinrich Schwabe, is the first sunspot cycle. It lasts about 11 years and is marked by the waxing and waning of sunspots on the surface of the Sun. At the peak of the cycle, an abundance of sunspots creates dark patches on the sun. As the cycle approaches its minimum, the frequency of sunspots decreases. Schwab cycles are repetitive but unpredictable. A cycle can be as brief as 8 years or as long as 14 years, and its intensity varies dramatically. The current solar cycle, number 25, began in December 2019. It is anticipated that solar activity will increase until the predicted solar apogee between 2024 and 2025. The second cycle, known as the Hale cycle, occurs twice as slowly as the Schwab cycle. The Hale cycle is particularly intriguing due to its emphasis on magnetic polarity. During this cycle, the magnetic field of the Sun reverses, with the north magnetic pole becoming the south magnetic pole and vice versa. At the commencement of a Hale cycle, magnetic field lines emerge from the northern hemisphere of the Sun. At the conclusion of the cycle, they reverse direction and emanate from the southern hemisphere. In other terms, the Hale cycle consists of two Schwab cycles with distinct polarities. In the universe, polarization reversal is a very prevalent phenomenon. The Earth's magnetic poles also reverse, but the interval between reversals is approximately 300,000 years. Last pole reversal occurred approximately 780,000 years ago. Last but not least, the Gleisberg cycle is a longer, approximately 88-year-long cycle that relates to the amplitude of sunspot activity over time. The Gleisberg cycle, while not as pronounced as the Schwab or Hale cycles, suggests more complex, long-term variations in solar activity. Researchers believe that interactions within the Sun's interior may influence this cycle, but research is ongoing. The potential effects of a solar storm in 2025. To begin with, it may interfere with your mobile devices. Possibly, you will be unable to use your phone for an entire day. Perhaps that will be an opportunity for us to experience life prior to the advent of social media. But how precisely does this work? Well, during a solar storm, an influx of charged particles from the Sun disturbs the Earth's magnetic field. This can induce electrical currents in Earth's conductive systems, such as power lines, pipelines, and even long metallic structures such as railways. In areas with reduced signal strength or in close proximity to power lines, mobile phones may experience interference or service disruptions. This interference may manifest as dropped communications, static on the line, or trouble establishing connections. Moreover, the increased levels of electromagnetic radiation during a solar storm can affect the electronic circuits in mobile phones. This could lead to transient malfunctions or diminished performance. However, every metal has two faces. During the solar maximum, you will have the best opportunity to witness spectacular auroras. Asking why? Well, this is quite simple to convey. Auroras occur when charged particles from the Sun collide with nitrogen and oxygen in the Earth's atmosphere. These collisions liberate energy as multicolored light. During a powerful solar storm, auroras may be visible at lower latitudes than usual, and occasionally even in regions where they are not typically observed. This means that individuals at lower latitudes, who rarely see auroras, may have the rare opportunity to witness these beautiful natural displays. Alright everyone, here is where the video ends. Thanks for watching. Is there anything you like to say? Tell us in the comments, and subscribe to the channel for more recent discoveries.